So to solve for the mass quality and temperature of the outlet stream, we're going to use the steam tables. Okay? And so, just to remind ourselves, we know the pressures and temperatures of each of the streams, or we at least know the pressures here. And we're also told if they're superheated or saturated. Okay? And so let's start with stream 1. We're told it's a superheated steam at a temperature of 500 degrees Celsius and 1 megapascal. And so what we're going to do is we're going to go to the back of our book. We're going to look up the superheated steam tables, and we're going to look for that pressure. So we want to find 1 megapascal, and that's listed here. And we're told a temperature of 500 degrees Celsius. Right? And so what we want to find here is the enthalpy value. And so there's the enthalpy value. It's listed, and it's in units of kilojoules per kilogram. H1 hat equals 3478.5 kilojoules per kilogram. Okay. All right, for stream 2, we know that it's at, we're only told the pressure, which is 0.1 megapascals. But we're also told that it's saturated, right? And we know that if we're told it's saturated, then we should go to the saturated steam tables. And since we're given a pressure, we're going to look at the saturated steam tables as a function of pressure. So what we want to find is the 0.1 megapascals, right? And if you're saturated and you're given a pressure, there can only be one temperature that corresponds to, right? That means you're at the saturation temperature, and in this case, the saturation temperature at this pressure is 99.63 degrees Celsius. Okay. We're also told the enthalpies of the vapor phase and the liquid phase as well. Okay. So let's write those down. So T2, 99.63 degrees C, H2V is this, H2L is this. All right, now for stream 3, we're told it's at a pressure of 0.5 megapascals. Okay? And so we're also told that it's saturated. And so in order to figure out the temperature, we could pull the same trick that we did for stream 2, where we just could look up the temperature. So now we know it's 151.86. And we could also look up the enthalpy values as well. 1.86 H3V 2748.7 kilojoules per kilogram H3L. Okay. All right. So now that we have all these values, what we could do is we could plug in our enthalpies into equation 1 over here. Okay. All right, so if we plug that in, we could solve for Q3, and we get the mass quality for stream 3 is 0.65. And so that says that 65% by mass of the outlet stream is in the vapor phase. You know, it's much higher than in stream 2. Okay. Once we have stream 3, we could then figure out M3V and M3L. Okay. All right, so by using the steam tables, that allowed us to figure out the mass quality of the outlet stream. For part B, what we want to do is now we want to figure out how much entropy is generated by this entire process. To do that, this is where we go to the entropy balance. Dealing with an open system, and so we'll use the open system entropy balance. We have our heat terms. And then we have Sgen. Alright, we assume the system was adiabatic, so we're not going to worry about any heats. But not only are we not assuming this process is reversible, we actually do want to go out and calculate Sgen. Right, so that's not going to be 0. But what is going to be 0 is the left-hand side, because this process is at steady state. Okay? And so if we expand out our entropy balance, we have this. And you'll notice that the entropy balance, just like the energy balance, also splits up into the vapor and liquid phases. Plus Sgen. And so, as it stands now, we want to figure out Sgen. And so the way to figure out Sgen, that means we need to figure out what each of these specific enthalpies are, or is. Fortunately, because we're dealing with steam, rather than having to go through a fundamental entropy calculation, instead what we could do is we could actually use the steam tables again. Because unlike in MEB2, where we only worried about internal energy, enthalpy, and specific volume, in your thermo textbook, it also lists the entropy values for steam. And so it's in this column here that I'm highlighting, right? And so the entropy here is going to be in units of kilojoules per kilogram Kelvin, right? We see it for the superheated steam, and we also have it for the saturated steam. The last 3 columns are for the entropy. And it's listed by the entropy in the liquid phase and the entropy in the vapor phase. This evap is just the difference between the vapor and the liquid. Right? That's all that is. Okay? All right, in any case, just like with the energy balance, we could just look up and record all of the entropy values for our different steam streams. So 7.7622. S2 for the vapor phase is this. We also have it for the outlet stream as well. Okay. All right, now that we have all of these entropy values, we'll just plug it into equation 2, which was our entropy balance. And what we get is that Sgen is equal to 3864.4 kilojoules per Kelvin. Right? Calculated Sgen, we have the value, but what we could also say is that this value is greater than 0. And so this tells us that the mixing of 2 different steam streams into one stream is spontaneous and irreversible. Right? So this tells us that the mixing of 2 different streams is something that will happen naturally without additional input of energy.